Welcome back to Software Engineering 2FA3 Discrete Mathematics with Applications 2. I am Bill Farmer, and this is going to be the last lecture of this series of lectures. We're going to begin by talking about the halting problem. So the halting problem is a problem of deciding whether a given Turing machine, let's say M, halts on a given input, let's say X. Now, the halting problem is semi-decidable. That means we can construct a Turing machine that will decide, semi-decide, when the Turing machine halts on the input. It won't be able to decide necessarily whether the Turing machine will not halt on an input. So how do we do this? We come up with a universal Turing machine, and we give it as input a code for M and a code for the input, and then we let U simulate M running on X, and if M halts on X, then we know that M will actually halt on X. And if M does not halt on X, we may not know that because it's very possible the simulation will run forever. So the halting problem is easily seen to be semi-decidable. But it's actually undecidable. That means we cannot come up with any total Turing machine that will be able to take be able to take the code for M and the code for the input for M and be able to determine in all cases whether that Turing machine will halt in X or not. So the halting problem is undecidable, and we're going to show this by diagonalization. This proof is similar to the proof that we use to show that there are uncountable sets that's due to Cantor. Okay, so let X be a string of zeros and ones, and if X is an encoding of a Turing machine whose input is zeros and ones, then let M of X be that machine. So we're going to restrict our attention to Turing machines whose input alphabet is 0 and 1. And MX will be the machine that corresponds to the encoding of this Turing machine. Now, if X is not an encoding of a Turing machine, we're going to let X be some trivial Turing machine that immediately halts on all strings all strings over the alphabet 0 and 1. So for every X, every string of zeros and ones, MX will be a real Turing machine. Now consider the following infinite two-dimensional matrix. So here we have all our Turing machines. These Turing machines correspond to strings of zeros and ones, so we have the simplest string, the empty string, the string of just 0, the string of 1, the string of 0, 0, and so forth. So down this column, we have all possible Turing machines, and on this row, we have all possible inputs. And so this matrix will tell us what happens with every Turing machine on every possible input. And H means that the Turing machine halts on the input, and L means the Turing machine loops on the input. So there exists some such infinite two-dimensional matrix. So now let's assume that K is a total Turing machine that has the following property. So K accepts this string, X sharp Y, if M of X halts on Y, and it rejects X sharp Y if MX loops on Y. So K's behavior then is going to be given by the following matrix. If X is a code for a Turing machine, and if Y is the input, and then A means that X accepts the string, and R means, I should say K accepts the string, and R means X rejects the string. And the thing to note here is if there actually were such a total Turing machine K, this K would solve the halting problem for all Turing machines whose input alphabet is 0 and 1. So remember, we're restricting ourselves to just Turing machines whose input alphabet is 0 and 1. So we're going to assume there is such a K. Now let D be the Turing machine that on input X runs K on X sharp K, and it accepts if K rejects, and it loops if K accepts. Now this makes sense because K is a total. Remember, K is a total Turing machine. And so D is going to be defined by the diagonal of K's matrix. So when K accepts, when K rejects, D is going to accept, and when it's going to loop when K accepts. So if we go back up here, what D is going to do is it's going to let's go back to this a moment. So K is going to accept if K rejects, and it's going to loop if K accepts. So it's going to, when along here, when K accepts, D is going to reject, and when K rejects, D is going to loop. Let's see, did I get that right? No, when K rejects, D accepts, and when K accepts, D loops. Okay, so now what we do is we know that D is a Turing machine whose input alphabet is 0 and 1, so it's going to equal MK for some X, some string X. And now D halts in X. Well, D halts in X means that K rejects. So that means K rejects this. And if K rejects this means that if we go back up what K does, K rejects this string if MX loops in Y. So this means if K rejects XX, that means MX loops on X. And MX is D. So this means D loops in X. So we've just shown that D halts in X if and only if D loops in X, which is an impossibility. This is a contradiction. So therefore, there is no Turing machine that solves the halting problem. So specifically what we've shown, there's no Turing machine that solves the halting problem for Turing machines with alphabet 0 and 1. So this is essentially what Turing showed. And this is one of the many important proofs in the theory of computation that uses a diagonalization argument. Okay, so now we're going to look at the notion of reduction. So with reduction, we have a set A and a set B. The set A is over some alphabet sigma, and the set B is over some alphabet pi. And we say we have a reduction, which sometimes we call it a many-one reduction of A to B, is going to be a total computable function from strings of sigma to strings of pi, such that X is in A if and only if sigma applied to X is in B. So basically this maps every member of A to a member of B, and the important thing here is that this is a total computable function. Okay, so we will say A is reducible to B, which we write like this: A is less than or equal M, and M means it's many to one. It's many to one because several strings in A can go to the same string in B if we want. Anyway, we'll say A is reducible to B if there is a reduction of A to B. And now we have a proposition 4, which says if A is reducible to B, then B is RE implies A is RE. So how do we know this is true? So let's assume A is reducible to B and B is RE. So if B is RE, there's going to be some M that accepts B. Some M that accepts B. And so we can come up with now a machine that will accept A. How does this work? The machine will, since there's a total computable function, there will be some machine for this function. I'll call it n sigma. And what we do is we give n sigma, and it will compute sigma, we'll give n sigma x, and it will compute sigma x. And then we'll give that sigma x to m, and it will compute whether it accepts that, whether that sigma x is in B. And if it is in B, then we know by the construction of this total computable function that x is in A. Therefore, we have a Turing machine that accepts A. And the same basic argument shows that if B is recursive, that implies that A is recursive. Now, there are many undecidable decision problems. They're not rare, they're quite common. And there's two techniques for showing that decision problems are undecidable. There's diagonalization and there's reduction. We've already seen how diagonalization works. We've showed that the halting problem is undecidable. So if x is a member of A is an undecidable decision problem, then by part 2 of proposition 4, we can show that x is a member of B is an undecidable decision problem by reducing A to B. So basically the idea here is if we know, so we have this statement, the contrapositive says that A is not recursive, implies B is not recursive. So we find an A that's undecidable, we reduce it to B, and then by this proposition, because A is undecidable, therefore it's not recursive, that means B is not recursive, therefore B is also undecidable. So by using reduction, we can show that other problems are undecidable by reducing to those problems we know are already undecidable. So to sum up, once we have some undecidable problems, which we show by diagonalization, then we can use reduction to show that many, many other problems are also undecidable. Okay, so this is our last slide of all our lectures. It basically sums up what we've looked at for the latter part of the course. And you've already seen this table. It's a table of languages, grammars, and automata. And we have 4 kinds of languages corresponding to the Chomsky hierarchy: regular, context-free, and context-sensitive, and recursively enumerable. And then we have 4 kinds of grammars: regular grammars, context-free grammars, context-sensitive grammars, and general grammars. And then we have various automata. For regular, we have DFAs, NFAs, and NFAs with epsilon transitions. For context-free, we have non-deterministic push-down automata. And for context-sensitive, we have linear bounded automata. And for RE, we have Turing machines. Now, the part in green deals with context-sensitive languages. We really haven't spent much time on these because they're not so important for computing as all the other languages are. We've also noted some subdivisions. So some context-free languages are linear. Those are languages that are generated by linear grammars. And there's also another subgroup of languages, deterministic context-free languages. Those are languages that are accepted by deterministic push-down automata. And another very important subset of languages of recursively enumerable languages are recursive languages. These are languages that are accepted by total Turing machines. Because they are accepted by total Turing machines, the Turing machine actually not only accepts the language, but it's a decider. It can decide whether a given string is a member of that language or not. So this completes the lectures for Software Engineering 2FA3. Thank you very much for your attention. Goodbye.